So in this segment, basically what we will see. So in this segment, basically, we will see that is the circular convolution. So after the end of the segment, students should be able to uh, express what is the circular convolution. So let me just start with uh, example. Uh, so up to now, we already covered the the DFT, right? So the DFT. So my question is, what is the DFT? So if you see that, if you have a signal, let's say this is your X of n, and you want to do a transform, let's say this is your DTFT. So 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 this is your DTFT. So if you do the DTFT, you actually get the capital X of omega, right? Capital X of omega. So in the time domain, if you see that your X of n is basically discrete, right? This is basically discrete, and let's say this is aperiodic. Let's say this is aperiodic. Okay, this is aperiodic. So if you do the DTFT, then you will get the X of omega. So basically, this X of omega is nothing but continuous, 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 and sorry, and periodic, periodic, and also the X of omega is nothing but complex. So this is complex number. So this is complex, right? Okay. So now if you consider another transform of X of n, let's say you have X of n and you do the transform, decide, okay, fine, I do a transform, and the transform is basically the DFT. That is the discrete Fourier transform. So this is your discrete Fourier transform. So if you do that, you basically get from here, that is your, for example, capital X of omega k, right? Capital X of omega k. So if you do the DTFT, then what will happen, right? Then what will be the case, or then what will be happening? So the so the DTFT basically you have a frequency spectrum of X of omega, whatever it may be. So basically you sample the frequencies, right? If you let's say I have a frequency response arbitrary. Let's say I have this type of periodicity in my frequency domain, and this is the periodicity of pi, and after pi the signal is basically again repeated, and at 2 pi we will basically the signal start from again. So this is the time period, so with a periodicity of 2 pi. So basically this signal is basically your absolute value, not absolute value. This is your X of omega. So if you consider the absolute value, then the negative part will be go towards to the positive part, right? So this is your X of omega, right? So now you consider the magnitude of X of omega. So the magnitude of X of omega is just simply if you consider the magnitude of X of omega, this will be just like, let me just change the color. So this will be, seems like this type of way, right? So basically this is your pi, and from pi there will be the same folding version is there. and then you will get again the signal is uh, periodic, because at the DTFT, if we do the DTFT, our signal is basically periodic with a periodicity of 2 pi. This is the feature. Basically, this is the feature of the x of omega. And if you do the magnitude of x of omega, it will be just even symmetric, right? So the even symmetric. So the same version at the at the negative side, actually also you have, right? So let me just consider here the x of k. So the x of k is basically nothing but you want to decide the sample the frequency. So if you do the sampling in the frequency domain, let's say you sample the signal, right? You sample the signal in terms of some values of n. If your the values of capital of n is higher, then you will get the best resolution. You will get the best resolution, right? So last class I actually show this situation, but in this segment, basically I actually uh, give a review of the concept. Okay. So this is your sampling frequency. So after the sampling in the frequency domain, your frequency is basically discretized. Your frequency is discretized. There is no continuity. So at x of k is now basically discrete. So the discrete frequency spectrum, right? So you have discrete frequency. You have discrete frequency, and your discrete frequency, but this is periodic, but but now but now but this is periodic. Argue periodic chilo, and now also this is periodic, right? But now this is actually discrete. So if you do the frequency sampling, then your x of n, it became periodic. At first time it will be aperiodic. Now this is periodic. So this is the impact of the DFT. If you do the DFT, we will get this type of change in the discrete time domain. So this is periodic, and this is basically discrete. It's basically discrete. So if you see that here, basically your frequency and your time index, they both are actually discrete now, right? So now let's consider you have a LTIC system. You have a LTIC system. So this is, say for example, your LTIC system. So you decided, okay, fine, I want to give the input is now x of n, right? But remember that now your x of n is periodic and discrete. Just remember these things. So you have an impulse response or the system response. This is also periodic. So let me just denote the periodic situation with a subscript p here. So p means it's periodic, right? So it's periodic. So it's simple that you will get an output that is y of n, right? That is so that is you get y of n, right? So the y of n is basically now also continuous. Sorry, it's my mistake. This is also periodic. So this will be periodic. But if you do the equation, if you want to write, you can write actually x of p of n, x of p of n. So it is basically very difficult. That is right with the mouse, and this is basically very hard work basically. All right. So you have x of p with with circular convolution. Sorry. Uh, so with circular convolution with h of p of n, h of p of n. So the convolution is very straightforward. That is, it is actually circular convolution. So this is not a simple convolution. This is not linear convolution. Now this is actually the circular convolution. So how do we can actually perform the circular convolution, right? So after go the segment, I basically show the x of omega. So this is y of omega k. So this is the frequency domain analysis, and this is actually capital X of omega, and multiplied with the impulse response domain transform, that is the transfer function. So this is the transfer function, and actually you can say that this is your filter response. So this is your filter response because you actually filtering the x of omega with multiply with the filter response, that is the frequency response. So this is your filter response. So this is your filter response. Okay. So my question is that now how do we can actually perform the circular convolution? So if you see that, I will give you an example, then everything will be clear to you. So let me show an example. How do we can perform the circular convolution basically? Okay. So at first I go to the circular convolution. Let me just show let me just show you a linear convolution. So at first I want to do a linear convolution that actually we covered in the after the midterm. Sorry, before the midterm. So linear convolution. Okay. So you need two signal. Let's say this is two signal is there. And two signal is there. Let's say you have x1 of n equal to let's say with a simple signal 1, 2, and 3, right? 1, 2, and 3. So the under there is actually means that this is your index n equal to 0. So what does it mean actually? So you see that you have n equal to 0 and then n equal to 1 and n equal to 2. So if you plot the signal, this will be nothing but this is your time index n, and this is your signal. Let's say I want to plot this signal, right? So x1 of n. So the n equal to 0, it actually implies that the center is here. You have 0. There is a sample, and the height of the sample is basically 1, right? And you have the time index n equal to 1. You have another sample, and your sample is basically your sample magnitude is basically or height is basically 2, and you have another sample at 2. The sample height is basically 3 here, right? Basically 3 here. And all the remaining other sample is basically, let's say 0. So let's say 0. So we can actually plot this discrete time signal by using this type of sample sequences if we have given. But if you see that here is no periodicity of the sample, this is a finite sample. So this is a finite sample, and this is your signal, and this is a discrete time signal. Okay, so let's consider we have another sample signal, which is x of 2 of n, right? X of 2 of n. So if you now let's say consider the signal actually 4, and then 5, and then let's say 6. So this is actually your sample signal. So at here you have the arrow again. So if you want to scale the signal, you can use this type of thing again. Then you can actually draw these things. So after now, if you see that you have two signal, let's say again I write here together. Let us signal x1 equal to 1 and 2 and 3, and under the signal I write to x2 of n This will be basically 4, 5, and 6. 4, 5, and 6. Okay, so this is your center, that is n equal to 0. This point is your n equal to 0. So now if you want to do the convolution, so the convolution is very straightforward. Let's say you have a new signal x of 3 of n. So this is basically nothing but x1 of n, x1 of n convolved with x2 of n, x2 of n. So if you see that here you have a convolution, right? So this convolution is basically now linear convolution. So we know all everybody that is what is the linear convolution. So we need a signal fixed. So let us consider x1 and is fixed. So actually I will see here a method. That method actually very pretty much help you to do this type of convolution. So at first I actually draw a cell, right? So this is my cell. So let's say you have this type of cell. So this is your x1 of n. This is 1 and 2 and then 3. Right, I just write down here x1 of n. And under this, I write here x2 of n. x2 of n. So if you see that, I just simply write down here x2 of n, that is 4 and then 5 and then 6 under the cell, right, under the cell. And this is your arrow where n equal to 0, and this is your arrow n equal to 0. So now basically I want to decide that I want to fix the x1 of n, but I want to fold x2 of n at first. So if you do that, you can actually write there is x2 minus n. x2 minus n. It means that you actually fold your signal. So if you see that here, this is n equal to 1, and this is your this is n equal to 0, this is n equal to 1, and this is your n equal to 2. So after the folding, your 4 in still is there. Your 4 is still there, but the 1 it is go to the minus 1. So let us draw here minus 1. So this is your 5, and your 6 now it will be go to the minus 2. So this is your 6. So if I write down here the index, this is your minus 1 index, this is your minus 2 index. So now your folding is done, and there all the sample is 0 because the cell is basically empties, right? Okay. So at n equal to 0, you want to I think the space it will be needed later on. So let me just clear this one. Okay, so let me just clear this one, and I use apart distance from here. Let's say this is good distance is there. So here this is n, and here this is for, let's say this is x of 3 of n, because this is our output, or this is our answer. So at n equal to 0, what is happening? So if you see that the multiplication, so you multiply this cell and 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 this cell, and individually you will sum up them. So if you see that now you have a 4 is there, and here is 1 is there. So you can basically write down here. 4 here, 4 times 1. So 4 times 1, and then plus here 0 times 2. So this is 0 times 2, and then here 0 times 3, right? 0 times 3. So let me just write down here plus 0 times 3. So you get just 4 here, right? So because these are 0. So at n equal to 0, you get 4, right? So now you do the shifting. So let's say you shift 1 samples, so n plus 1. So n plus 1 you do the shifting. So I just extend the cell again. So your 4 is now basically go here, and the 5 it is entered to the cell. So the 5 is going here, and the 6 is now there, and this sample is basically 0, right? So now you multiply with x of 2 n minus n plus 1 with x of 1 of n. So if you see that, now you can do the multiplication again. So let me change the color. Let me change the color. Okay, so now you have 5 here and here again 1, right? Again here 1. So you can write that. You can write that at n equal to 1, n equal to 1, you have 5 times 1. So this is 5 times 1, and then you have plus, and here you have 4 and then 2, so it will be 4 times 2, 4 times 2, and then plus you have 0 times 3. So this 0 times 3. So basically it will be 5. 5 times 1 is 5, and 4 times 2 is 8. So it is actually 13, right? So this is actually 13. So this is the case of your at n equal to 1. So now you do the again the shifting. So x2 minus n plus 2. So it means that you shift or delete the 2 samples. You delete the 2 samples. So basically now the 0, this 0 is now here, and this 0 is outside is there. So the 4 is now here, and the 5 is now here, and now that is 6. So this is the second shifting. You delete the 2 samples, right? You delete the 2 samples. So at n equal to 2, what should you can write? So if you see that here, you have 6 and here 1, because the index is same, so same index multiplied with each other. So you can write here 6 times 1, 6 times 1, and then use a plus sign, and here 5, and here is 2. So 5 times 2, 5. So here is 5 times 2, and you have here 4 times 3. So use here plus sign, and then write here 4 times 3. 4 times 3. Right. So you have here 6 plus 10 and plus 12. Plus 12. So this is basically 28. Right. So this is basically 28. So this is 28. Right. So this is the situation of at n equal to 2. Now you decide, okay, fine, I do again the sampling. Sorry, I again do the shifting. So this is your x3. Sorry, it's my mistake. It is actually not x3, right? So this will be x of 2 and minus n plus 3, right? Minus n plus 3. So let me just mark out the situation. Mark out the situation in terms of shifting index, basically, right? Shifting index basically. So this is your x of minus n. This is the first shifting. This is the second sample delays, and now we want to delay the third sample. So if you delay the third sample, the 4 is out of the shell. The 4 is basically out of the shell. So now the 4 is from out of the shell. So the 5 is there. So the 5 is there, and the 6 is here, and there is 0, and you have 4 is there. So this is basically out of the cell, right? You see that the shell is now out of the 4. Now is out of the shell, and this is your x2 minus n plus 3 situation, basically, right? So now you want to decide, okay, fine, I want to write the situation at n equal to 3. So you have again you have 0 and you have 1. So let me just multiply these things. So 0 times 1 plus here 6, and here is 2. So 6 times 2 plus here is 5, and there is 6. So this is basically 5 times 6. 5 times 3. So here is basically 0, and here is 12, and here is basically 15, right? So 15 plus 12 is basically nothing but 27, right? So this is basically 27. Okay, so now you want to do again, the third sample is basically is remaining, so you need to shift in at n equal to 4. You decided that I need to shift again n equal to 4, because your sample is again still there is your samples, and you can perform the convolution, because the convolution is don't end up to now. The process is actually running, right? The process is actually not finished or not end. It is actually running. So you again write here, for this reason, x x2 x2 minus n plus 4. That is a 4 sample delay. You want to decide that. Okay, you want to decide that the 4 sample delay. So this is the 4 sample delay situation. So here the 5 is actually now out of the shell. So now here is 5 and the 4 is there. So here is 6 and all the remaining sample values basically 0. Basically 0. Right. So now you again do the multiplication. Again do the multiplication. So if you see that at n equal to 4, you have 0 and here is again 1. So here is again 1. So let me just write down here. So 0 times 1 plus 0 times 2, because there is 0. Sorry, there is 2. So 0 times 2, and then you consider here plus 6 times 3. So 6 times 3. So after do the calculation, you get here 18. Right, 18. All right. Sorry, so I think there is a mistake. There is a mistake. Let me just clear this one. Okay. So the linear convolution is not finished. So again you need to delete the sample. Again you need to delete the sample. So this is your last. Right. 6 2 minus n plus 5. Basically you do the shifting the 5 sample delay now. So what does it mean actually? So it is actually means that you again delay your samples. You delay your samples. So now the 6 is actually out of the shell. 5 is here and 4 is there. So if you see that here is 0 and 0 and 0, if you multiply all the 0, it means that at n equal to 5, you have 0. So it means that your linear convolution is finished. Okay, your linear convolution is finished. So you have your all the samples data at the output of the x3 of n, which is your convolution result. So now if you want to write your convolution result, it is basically nothing but x3 of n is equals to here is 4, here is 13, right? 13, and then 28. So this 28, and then you have 27, and then you have 27. So this is your 27, and you have 18, and your next all the sample is basically 0. So you need not to write down this one because all the sample is 0. So this is your answer, and this is your linear convolution output sample sequences in this cases. And this is your arrow because this is n equal to 1, n equal to 0, because you have get n equal to 0, the value is basically 4 here, right? So if you see that here, your output sequences is basically 6. Your output sample sequence is basically 6. Your length is 6. Your length is 5. Your length is 5. It's my mistake. Your length is basically 5, right? Your length is basically 5 here. So you can actually before you can actually calculate your length of your output sequence, because you have x of 1 of n x1 of n. So if you see that your x1 of n, the input signal you have x1 of n, so your length is basically here 3 because you have 0 1 2 3, so your length is basically 3. So x1 of n signal length plus x2 of n signal length, so this is actually also here 3 if you count that. This is also actually 3, so 3, and the formula you have -1, so you have 6, you have 6 minus 1, so you have 5. So this 5 is actually your length. So you can satisfy by using the formula, either your length is actually cover this condition of the output, so you can write this, that's actually fine, and this is your answer, and this is our answer. So this is the concept of the linear convolution. So if you see that your linear convolution, if you consider is there, your linear convolution here actually your x1 of n and x2 of n, they both are actually aperiodic. Right? Aperiodic. Right. And your output is actually also aperiodic. But whenever you do so this is the case of the DTFT. So the DTFT that gives you the linear convolution. But if you do the DFT, so then the concept is actually not like this type of convolution. The convolution situation is basically changed. That situation is basically known as the circular convolution, because if you do the circular convolution and if you do the DFT, now your x1 of n and your x2 of n, your both two signal is basically now periodic. So now your x1 p of n is basically it indicates that your signal is now periodic, right? So your signal have a periodicity. So initially your signal was 1, and there is 2, and there is 3, right? And this is your arrow, for example, at n equal to 0. But if you see that now at the negative index, you have 1, 2, 3, and this is goes on because this is periodic, and then you have again 1, 2, 3 because this is periodic signal, right? And this have a periodicity, and it goes so on. It is periodic actually, Taina. So if you see that you have now x2 periodic signal of n, and your 4, 5, 6, your 4, 5, 6, and again I want to write down here. So this is your 4, 5, 6, and this is your again 4, 5, 6 is there. So this is your 4, 5, 6 again, and it goes so on. And at the left hand side, this is also goes on the left hand side because the signal is basically periodic, right? The signal is basically periodic. So if you say that this is your index, and your x of 1 of n p and x of 2 p, these two signal are basically now periodic. So if you want to do the convolution and the DFT, you doesn't get x3 of n with the linear convolution because it is actually all time convolved with each other, right? So let me just write down here x3 p of n, because you get the x3 p of n also the periodic signal, right? So this is actually nothing but x1 of n p of n in the time domain is x1 of n 2 of periodic n is actually basically nothing but the circular convolution with the x2 of n. So how do we actually perform the circular convolution? So this is the last topic of today's class, right? So how to actually we can perform the circular convolution. So we discussed the linear convolution, but it is actually pretty much you know that it is actually different, quite different, because your signal is now aperiodic, not aperiodic, it is actually periodic. So actually I actually invention a technique. So this technique is basically I want to show with you or share with you. So this is the technique. So at first you write your signal x1 of n. So x1 of n. So x1 of n. But remember that your signal x1 of n is basically now periodic, right? Now periodic and also discrete. Okay. So at first, again, the rules is same. The rules is not different. The same rule we actually apply for the circular convolution. So you need a fixed signal. So if you consider a fixed signal, you actually write down the fixed signal with your pen, not pencil, pen. So 1, 2, 3, right? And then again you maintain apart the distance. Let's write here 1, 2, and then 3. So I think this apart distance is not pretty much good. So let me just erase this and create this type of apart. So this is the technique. All right. So then you write again 1, 2, and 3. Okay. So now you divide these things in terms of this type of division, and this is n equal to 0 because this is your center at n equal to 0. So this x1 of n, you want to decide, I want to fix the signal. So far, what is the happening? What is the problem? Oh my God. কি সমস্যা হলো, এটা সব গায়েব হয়ে গেছে। আচ্ছা যাই হোক, এখান থেকে আবার দেখাই দিই। আচ্ছা আমরা সার্কুলার কনভলিউশন করতেছিলাম, তো যাই হোক, তো আমাদের x1 of n এটাকে আমরা ফিক্সড রাখতে চাচ্ছি। তো এখানে থাকবে হচ্ছে 1, 2, 3, এখানে থাকবে হচ্ছে 1, এখানে থাকবে হচ্ছে 2, এখানে থাকবে হচ্ছে 3। তো আমরা এই x1 of n, এই প্রথম সিগন্যালটাকে আমরা ফিক্স রাখবো। তো এই কারণে আমরা এটাকে কলম দিয়ে লিখবো। হ্যাঁ, এটাকে আমরা কলম দিয়ে লিখবো। আর এটা নিচে হুবহু সেম ভাবে x2 of n এই সিগন্যালটাকেও লিখে ফেলবো। একবারে যেটা দেওয়া আছে ওটাকে পিরিয়ডিক বানায় যদি সার্কুলার কনভলিউশন বলে, জাস্ট হুবহু নিচে সেল বাই সেল লিখবো 4, 5, 6। হ্যাঁ, 4, 5, 6, 4, 5, 6। Okay. So here it is actually this is your n equal to 0. So আমি জাস্ট সিম্পলি তাদেরকে লিখে নিছি, আর কিছু না। তো যেটাকে ফোল্ড করব সেটাকে পেন্সিল দিয়ে লিখতে হবে। তো আমি উপরেরটাকে ফোল্ড করব না, ফিক্সড রাখবো, তাই ওটাকে কলম দিয়ে লিখবো। আর এটাকে ফোল্ড করব, তাই এটাকে পেন্সিল দিয়ে লিখছি আমি। আর আরেকটা কাজ করতে হবে, এটার ইন্ডেক্স গুলোকে একটু মার্ক করে দিতে পারো। n equal to 0, n equal to 1, n equal to 2। ঠিক আছে, পজিটিভ। ঠিক আছে, আর নেগেটিভ সাইডে এটা হচ্ছে -1, এটা হচ্ছে -2। আচ্ছা, এখন আমি নিচের সিগন্যালটাকে ফোল্ড করতে চাই, উপরেরটাকে যেভাবে আছে ওভাবে রাখবো। সো ফোল্ড করতে চাই। সো ফোল্ড করার জন্য আমি n equal to 0 কে তো কিছু করতে পারবো না, তাই না? তো আমাকে যেটা করতে হবে সেটা হচ্ছে এই 1টাকে ফোল্ড করে এদিকে নিয়ে আসতে হবে। ফোল্ডিং এর মানেই হচ্ছে তাই। ঠিক আছে, আর n equal to 2 এটা চলে আসবে হচ্ছে -2 তে। ঠিক আছে, সো ফোল্ড করার পরে সিচুয়েশনটা কি হবে সেটা আমি একটু লিখে দেখাই। তো আবার উপরের সিগন্যালটা যেভাবে আছে একবারে হুবহু সেইভাবে কলম দিয়ে লিখে ফেলো 1, 2, 3, 1, 2, 3। and again আরেকটু ডিসটেন্স মেইনটেইন করে এখানে লিখে ফেলা হচ্ছে 1, 2, 3। ঠিক আছে, আর এখানে হচ্ছে তোমার ওই অ্যারোটা ছিল, মানে তোমার পিরিয়ডিক, অর্থাৎ এখানে ইন্ডেক্স হচ্ছে 0। সো এখন ফোল্ডিং করব, ফাইন। একের নিচে 4 আছে, এই যে এখানে আমরা যদি খেয়াল করে দেখি এটা যেভাবে এখানে আছে এটাকে এইভাবে এখানে রাখবো, এই সিচুয়েশনটার জন্য বলতেছি। সো 1 এর নিচে 4 আছে, জাস্ট সিম্পলি আমি 1 এর নিচে মানে এখানে মানে 4 বসাই দিলাম। আচ্ছা, এখন দেখি এখানে ফোল্ডিং করার পরে কি হচ্ছে। সো +1 ইন্ডেক্স আছে হচ্ছে 5 আর -1 ইন্ডেক্স আছে 6। তার মানে 5 +1 ইন্ডেক্স থেকে -1 ইন্ডেক্সে চলে যাবে, তাহলে 2 এর নিচে আসবে হচ্ছে 5। 2 এর নিচে আসবে হচ্ছে 5 আর -1 এর 6 ভ্যালুটা চলে যাবে +1 এ। সো এখানে 4 থাকবে, বাই ডিফল্ট 4 থাকবে, কারণ এটাকে তো আমরা চেঞ্জ করছি না। সো 5টা আসলে বাম পাশে চলে আসলো, 6টা +1 এ চলে গেল। ঠিক আছে, 6টা 5 এখানে যদি চলে আসে 4 5 6, so I think it is right or wrong. So 5 is here, 4 5 6, so -1 -2 +1 +2, right? So 5 is now at -1. So yes, I think there is a mistake because this is not -2 index, because this is -2 index. This is not +1 index, -1 index, right? মানে আমি বলতে চাচ্ছি হচ্ছে আমার মাইনাস মানে +1 ইন্ডেক্সে যে স্যাম্পলটা আছে সেটা -1 স্যাম্পলে যাবে। তো -1 স্যাম্পল তো এখানে, কারণ n = 0 যদি এটা হয়, হ্যাঁ, n = 0 যদি এটা হয়, তাহলে এটা হচ্ছে +1, হ্যাঁ, তাহলে এটা -1 হবে না। তো এটা -1 হলে এখানে কি আসবে, আসলে এখানে 5 চলে আসবে। ঠিক আছে, এখানে 5 চলে আসবে। আচ্ছা, এখন খেয়াল করে দেখি 6 +2 তে আছে, সো এটা -2 তে চলে আসবে। সো এটা যদি -1 হয়, এটা হচ্ছে -2, সো এটা হচ্ছে 6, আর এখানে 5 এ চলে আসবে। সো আমি কিন্তু আমার ফোল্ডিং করার পরে পিরিয়ডিসিটি পেয়ে গেছি অলরেডি। সো এটা হচ্ছে 4 6 5 4 6 5। সো এর নিচে আসলে আমাকে লিখতে হবে হচ্ছে 4 6 5। 4 6 5। তো সুবিধার জন্য আমি ইন্ডেক্স নাম্বারগুলো চাইলে পরে পেন্সিল দিয়ে মুছে দিতে পারি। মুছে দিতে পারি, ঠিক আছে। তো ফোল্ডিং করার পরে এই হচ্ছে আমার সিগন্যাল। এখন এই দুটোর মধ্যে আমাকে কনভলিউশন করতে হবে, ঠিক আছে। এই দুটোর মধ্যে এখন আমাকে কনভলিউশন করতে হবে। আচ্ছা, ঠিক আছে। সো আগের মতোই আমি এখানে রেজাল্ট রাখার জন্য একটা জায়গা তৈরি করি, n, আর এটাকে দিচ্ছে হচ্ছে x3 of n, x3 of n। সো n = 0। হ্যাঁ, তো এখন কি হবে? সো at n = 0 আমরা শুধুমাত্র এই বক্সটা নিয়ে কাজ করব, তাহলেই হবে, কারণ যেহেতু এটা পিরিয়ডিক, সো একটা পিরিয়ড নিয়ে কাজ করলেই হবে। তো আমরা শুধুমাত্র এই মাঝখানের জায়গাটা নিয়ে কাজ করব, যেহেতু পিরিয়ডিক, সো একটা পিরিয়ড ধরে কাজ করলেই হয়। সো n = 0 তে কোনো ফোল্ডিং টোল্ডিং কিছু নাই, একবারে ওভারল্যাপড অবস্থায় আছে। 4 এর সাথে 1 গুণ হবে, তো 4 একে 4 হবে, ঠিক আছে, প্লাস 6 দুগুণে 12 হবে, আর 3 5 15 হবে, ঠিক আছে, 3 5 15 হবে। তো এগুলো যোগ করলে হবে হচ্ছে 31, 31। সো n = 0 তে তুমি 31 পাইছো। আচ্ছা, আমি যে টেকনিকটা ব্যবহার করব সেটা আমি শেয়ার করব। সো টেকনিকটা হচ্ছে n = 1, তো শিফটিং হবে, ঠিক আছে। তো শিফটিং হোক, দ্যাট ডাজন্ট ম্যাটার। তো শিফটিং যখন হবে, এই 5টা এখান থেকে বের হবে, এ ঘুরে এসে এইখানে ঢুকবে। হ্যাঁ, তো এখানে তুমি দিতে পারো হচ্ছে 1, মানে তুমি একটা স্যাম্পল শিফট করলো। তো 5 ঘুরে এসে যদি এখানে হয়, তাহলে 5 এখানে চলে আসলো, ও ঠেলে 4টার এদিকে নিয়ে আসলো, তাহলে এখন হলো 4। হ্যাঁ, তো 4 যদি এদিকে হয়, তো 6 আবার ঠেলে 5 কে বাইর করে দিছে। সো এখানে 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 6টা চলে আসবে। এটা হচ্ছে n = 1 এর সিচুয়েশন। তো এখন তুমি n = 1 এর এই 5 এর সাথে এবার 1 কে গুণ করো, ঠিক আছে। তো এটা হচ্ছে n = 1 এর জন্য। হ্যাঁ, n = 1 এর জন্য। তো 5 একে 5, ঠিক আছে, 5 একে 5 যোগ পরের স্যাম্পলের জন্য 4 × 2, তার মানে হচ্ছে 4 দুগুণে 8, প্লাস 3 6 18, ঠিক আছে, 3 6 18। তো 18 আর 8 আর 5 এটা যোগ করলে হয় হচ্ছে তোমার 26 আর 5 31, 31 31। সো n = 1 এ আমরা 31 পাইছি, ঠিক আছে। এবার n = 2 এর জন্য করব, রাইট। তো n = 2 এর জন্য কি হবে? अगेन এবার 6 কে টার্গেট করো, এই 6 এখান থেকে বের হয়ে ঘুরে এদিকে ঢুকবে, ঠিক আছে। এটার পাশে একটু 2 লিখে রাখো। তো 6 এখন এখানে চলে আসছে, তো 5 এখন চলে আসবে হচ্ছে এখানে, আর 4 এখন চলে আসবে হচ্ছে এখানে। তো এই হচ্ছে সিচুয়েশন, ঠিক আছে। তো এবার এই 6 এর সাথে 1 কে গুণ করো, তো 6 1 কে 6, ঠিক আছে, 6 1 কে 6 প্লাস 5 দুগুণে 10, কারণ আমি মানে এই 2 এর সাথে 5 কে গুণ করতেছি, তাই 10 হলো, 5 দুগুণে 10, আর হচ্ছে 4 এর সাথে 3 যোগ করতেছি, 3 4 এ 12, হ্যাঁ 3 4 এ 12, সো 12 10 এ 22 আর 6 28, তো n equal to 2 তে তুমি পাচ্ছ হচ্ছে 28। এবার n equal to 3 এর জন্য চিন্তা করি। So at n equal to 3, if you see that you now have 4, right? You have 4. So এখন এই 4টা ঘুরে এসে এবার এখানে চলে আসবে, সেটা হচ্ছে 3। So 4 যদি এখানে হয় তাহলে 6 এখানে চলে আসবে আর 5 এখানে চলে আসবে, ঠিক আছে। So already you have 465, you have 465, কারণ 465 তোমার অলরেডি বের করা আছে। তো 465 এর ভ্যালু কত? তো 465 একেবারে n equal to 0 তে পাইছিলাম, তো 465 n equal to 0 তে হচ্ছে 31, তাই না? তো তুমি বললা ওকে ফাইন, আমি n equal to 4 এ দেখতে চাই। সো 4 এর বেলায় কি হবে, ঠিক আছে। সো 4 এর বেলায় যেটা হবে, এই 5টা ঘুরে এসে আবার এখানে চলে আসবে। তো 5 যদি এখানে হয় তাহলে 5 4 6, এখানে 5 চলে আসবে, 4টা এখানে, 6টা এখানে, 5 4 6। তো খেয়াল করে দেখো 5 4 6 এর ভ্যালু তোমার এখানে অলরেডি আছে, দ্যাট ইজ 1, তার মানে n equal to 1 এর জন্য তোমার অলরেডি আছে, করা লাগবে না। সো দিস ইজ again 31, again 31. So if you see that this actually repeating, তাই না, এটা রিপিট করতে থাকতেছে, মানে তোমার এই সিচুয়েশনটা এখান থেকে শুরু করে এই পর্যন্ত এই সিচুয়েশনটা রিপিট করতেছে। ফলে এখান থেকে আর কোনো করার কিছু নাই আমাদের, এখান থেকে যেহেতু আমরা রিপিটেশন এক পিরিয়ডের জন্য পেয়ে গেছি, আমরা এখান থেকে আনসারে চলে আসতে পারি। সো দ্য আনসার উইল বি x, সো 3 of n, x3 of n is equals to x3 of n is equals to let us write 31, and then again 31, and then 28, 28. So this is again 31, and 28, and it is actually goes so on, right? It is actually goes so on because this is periodic. Okay, so this is periodic. So n equal to 0, you get 31. So this is your at n equal to 0. So the arrow is actually, we consider there. So basically this is your circular convolution answer, and you can see that your output is actually all time it is convolved with each other, because your the x1 of n and x2 of n, the both two signal is basically periodic. So far your output is periodic. It means that a circular convolution, it contains running all the times. Okay, so far you get that this type of circular convolution result. So here is the one observation we have. So the observation is very simple. That is, the observation is very simple. That is your input signal length and your output signal length, they are basically same. So if you see that your x of 1 of n, its one period length was 3, and now this is actually 3. So this is your answer. That is the first sample x1 of n. It was 1 2 3. So this is your arrow. So this is the length is 3 and this is length is 3. So linear convolution এর জন্য আমরা যে রেজাল্ট এর জন্য যে লেন্থের ক্যালকুলেশন করছিলাম, এটা এখানে পিরিয়ডিকের জন্য খাটবে না, ওটা যেটা হবে সেটাই আসবে। সো দিস ইজ দ্য সার্কুলার কনভলিউশন, আমরা যেটা একটা এক্সাম্পলের মাধ্যমে দেখার চেষ্টা করেছি। সো ইন দিস আই অ্যাকচুয়ালি কনক্লুড দ্য সেগমেন্ট। থ্যাংক ইউ।